population, it's obvious. Sample, it's obvious. Parameter, what's parameter is the, when you talk about statistics, we talk about mean, standard deviation, sum of square, all of these things. But we're usually talking about statistic because we are working on a sample. But what if sample is the entire population we're interested in? If we don't have to sample the population, but we can actually get all the data from the entire population, then what we get is not a statistic, it's a parameter. It's just a terminology thing. So statistic is the calculations and the data from the sample, but parameter is calculations and all the kind of values from the entire population. So we want parameter, but we can't get it all the time. So we we work on whatever we can get, which is always usually a sample. Because the entire population usually consists of like millions of billions of people. Let's see, if you're gonna get a population from our university, we're gonna have to get data from all the 30,000 students, for example. But we can't, so we kind of handpick. We pick sample population, like maybe 50, 30. That's like very small portion of the entire population, but we get the data from whatever, the limited number of people we can gather data from, and we do calculation, and the value we get is statistics. Okay, let's look at, and this is an example we covered. Okay, if you want to know all the average IQ of American college students, if you want to get the absolute data, absolute average, based on the entire population, entire students, American college students, you're gonna have to measure the IQ of all American college students and get the average. Then you can get the absolute IQ, which is called parameter. That value is not a statistic anymore because it's coming from the entire population, and you call it parameter. Average on parameter is called mu. Okay, this is mu. It's like a Greek letter for M. Okay, and okay, you can't measure all the college students in America, so I randomly select 50 and measure their IQs. That's what sampling is. That's what statistics is about, because you can't measure the entire population. So you randomly select 50 or a certain number of people and measure their data. So sample is 50 American college students, and statistic is the average IQ of the 50 college students in your sample. And sample mean is denoted by capital M. Let's look at example 2. I want to know the population of Nebraskan voters who plan to vote Democrat in 2012. So ideally, what we want is parameter. How many Nebraskan voters we have in Nebraska? So many, and though it might be possible to get give questionnaires to every single voter in Nebraska and get a result from them, chances are we're not going to be able to do it. So, but we could get some responses from certain number of people. Obviously not the entire people, or not even half the population, but some people, like 150, I don't know. So it's doable. So in that case, let's see, I can't ask all Nebraskans who they plan to vote for, so I randomly say 100 and ask them. Okay, so we ask only 100 out of entire Nebraskan population. 100 Nebraskan voters. That's very small, but that's what statistics is about, because you can't really handle all that, maybe, but while you're gathering data, things might change. So yeah, it might take years, and it's too late. If you want to gather data from every single Nebraskan voter, there's a timing issue. What if it takes 3 years? Then the first, the data you got for the first 1 year, and the last 1 year, you can't combine them, because things change. So okay, so there's a limit to physical limitation. That's why sometimes we have to resort to statistics. And let's see, 100 Nebraskan voters, we get it in a month or so. Okay, then population of 100 Nebraskan voters in my sample who plan to vote Democrat in 2012. You can get that. And okay, here what I would like to mention is the population. Okay, the parameter for the population is pi, and sample population is denoted by lowercase p, pi and p. Okay, so whenever it is a Greek letter, it's usually a parameter, and when it is a Roman letter, it's a sample statistic, values. The main points here is there are 4 main points. The practice of okay, this is called inferential statistics. It's about using information in a sample to make inferences about population. That's what I've been talking about. What we are doing, taking sample instead of getting the value calculations on the entire population. So population data are rarely available, so population parameters are rarely, if ever, known. Sample statistics are estimates of population parameters that are subject to all kinds of error. Okay, and much of what we do in this course would involve figuring out how much error we should expect sample-based parameter estimates to contain. Doing so will allow us to draw more responsible conclusions about the populations we are interested in. So there are errors because we are working on a sample, not the entire population. Think about even a simple average, mean. If we know if we can measure entire population and try to get the average, which is a mu, that's the true, absolutely, correct average of the entire population. But when we get 50 samples out of all the population, and if we get the average of the sample, which consists of only 50 people, if the entire population is 1 million, then if you only get 50 people as a sample, the average you get, most likely not going to be the same with the mu. Okay. They might be close though, but not the same. And sometimes there are huge error. Some one value or a couple of values may throw off the entire calculation, and so there are errors, and we try to figure out how much error is okay, how much error is not okay. And there are some statistic evidence that the certain errors, if it falls within a certain errors, it's okay, and if it goes way off, then you know, or things like that. So this is what we covered in our first day, on our first day. Okay, more to come.